In this video, we're going to learn a little about using a TDS or total dissolved solids meter to check the quality of reverse osmosis product water and learn a little about the accuracy of TDS measurements. I use this little meter here. I bought it off Amazon, real inexpensive, about $13.89. I believe that included shipping. And you can find that very easy. All different manufacturers of them. This was actually the least expensive thing I could find, and it actually works pretty well. Dissolved solids are those solid materials that can dissolve into water and cannot be easily filtered out with conventional sand or other filters. Non-dissolving solids are aqueous suspensions of clay, sand, and other inorganic and organic materials that can be easily flocculated, settled out of suspension, and filtered out. Non-volatile contaminants, whether dissolved or present as a suspension, can be measured gravimetrically by weighing the water, then boiling the water away, and then weighing the solids left in the pan. Total dissolved solids meters are essentially conductivity meters that make it easy to measure dissolved solids that ionize into plus and minus ions. Okay, this is the total dissolved solids meter. It's reading 0 ppm or parts per million, which it should. It's not in anything, just sitting here in air. Now, if we take this and look at the bottom of it, see those metal pins? There's 2 pins to the right. They're electrodes. So the idea is it's going to measure the conductivity in the solution between those electrodes. Let's just put it in some distilled water here and see what happens. Well, we're still reading 0 because there's nothing in the water. It's pretty pure. It's distilled. So let's take this a step further. What's really going on between those electrodes? Okay, how does a total dissolved solids meter work? This is showing what a meter might look like. Got a display here reading in parts per million. That's a part in per million, or 1 part contaminant in a million parts total, ppm. We're showing AC voltage on here, minus and plus electrode, but with AC that's going to oscillate back and forth. Minus, plus, minus, plus, minus, plus, minus, plus. This just arbitrarily shows it in one configuration. Here, plus here, minus here, but it's oscillating between polarities. And just miscellaneous plus and minus ions in of dissolved ions in solution. Now, when a voltage is applied to the electrodes, positive ions are attracted to the negative electrode and negative ions attracted to the positive electrode. That's what we're showing here, positive here, minus here. It's important to know that if this had a DC voltage, if that was used, the ions would migrate to the electrodes, and then as the electrode surface became covered with ions, current would stop, and similar to a capacitor, unless the voltage was so high electrolysis occurred. This won't happen with an AC voltage since the electrodes are oscillating continuously between plus and minus at a speed proportional to the frequency of the applied voltage. Now, only solids that dissolve and form ions in solution can increase the conductivity of water. There aren't loosely held conduction band electrons like we have in metals. What this means is solids that do not dissolve into ions will not be measurable by a total dissolved solids meter. This is 1/4 teaspoon. We're going to measure out 1/4 teaspoon of Morton iodized sea salt and put it in 175 milliliters of water. That's distilled water. All these are distilled water. That's it right there. Okay, and we're going to clean off the tables, the 1/4 teaspoon measurement. Do the same thing with table sugar, which is sucrose. Put that in, same amount of water, 175 milliliters of distilled water. Clean it off. Do the same thing, a level teaspoon of 70% isopropyl alcohol, and put that in the water. We're going to get a little sample. Typical South Carolina red dirt. Here we go. That's all we need. And this is just plain old South Carolina red dirt. We're going to do the same thing, level quarter teaspoon, put that into the water. Stir them up real good, let them shake overnight, or excuse me, let them stand overnight and make sure everything's dissolved as much as it's going to. Then we'll use the total dissolved solids meter and see what they look like. I think it's going to be interesting. Okay, here's the setup. 175 milliliters of liquid water in each of these mason jars. This one I've got distilled water plus salt, distilled water plus sugar, distilled water plus rubbing alcohol, isopropyl alcohol, distilled water plus just plain old South Carolina red dirt, just our tap water, which is a city water, tap water purified by RO called their product water, and this is the RO discharge water. Here's the plan. I'm going to take this total dissolved solids meter, turn it on, dip it in each one down to about 1.5 inches or so, what they recommend, no further than that, and take a reading. Then I'm going to wash it off over this pan with distilled water, because I know it's clean. Okay, I got distilled water in that and this. I'm probably going to use this squirt bottle here. And then I'll shake off that water and put it in the next one. Take a reading, and I'm going to say the reading and probably write it down on these cards, and we'll see what we get. Okay, this is our distilled water sample. We're reading 0. We'd expect that. There shouldn't be much in it. Okay, this is our 1/4 teaspoon of salt, distilled water. We'll click on hold. Got 1,472, sky high. Wash that salt out of there real well. Clear the reading. Now this is our distilled water plus 1/4 teaspoon of sugar. One, very low. I would have expected that. Well, sugar doesn't ionize too easily. I'm going to repeat some of these. That's why there's already a number on here, 1, because you couldn't see what I was doing in the first attempt at this. This is distilled water plus 1/4 teaspoon of rubbing alcohol. Okay, let's clear this thing. It's cleared. Put that in. We get a 1. Same thing as we got the first time. Okay. Wash it out. Okay, this is our distilled water plus red dirt, good old South Carolina red dirt, 1/4 teaspoon and 175 milliliters of distilled water. Let's put that in there. 1. Red dirt apparently doesn't ionize too easily. Let's wash that out real good. Okay, this is our tap water sample, just plain old city water, or local city water. We cleared this and washed it off. 22, 23. Slightly higher than I got the first time. Yep. Okay. Okay, we'll clear. This is our tap water, purified by our RO system. Got 2 the first time I did this. Let's see what we get this time. 2. Same thing. So it went from 22, 23 to 2. Big difference. Okay, this is our RO system discharge water. This is the excess water that goes down the drain. 23, same thing I got the first time. Really about the same as the tap water. All right, that's okay, that's the discharge water. Let's summarize these results and we'll go over it. Okay, this is the results of our experiment to demonstrate the effect of ions on TDS measurements and testing the purity of our reverse osmosis product water. For distilled water only, we got a reading of 0. Distilled water plus quarter teaspoon of salt, sodium chloride, we had 1472, a sky high reading. Distilled water plus quarter teaspoon of sucrose or table sugar, just a 1, hardly anything. Distilled water plus 1/4 teaspoon of isopropyl alcohol, rubbing alcohol, a 1. Distilled water plus 1/4 teaspoon of South Carolina red dirt, we got a 1. Tap water from our city water department, we had 22 to 23, not high, but it is measurable. Tap water purified by our reverse osmosis system, we just got a reading of 2. Discharge water from the reverse osmosis system, wastewater down the drain, was 23. About the same as original tap water. I think it was slightly higher. It should be, but it's very dilute, so that's why it won't be much different. Okay, let's summarize what we got. The distilled water had a very low reading. It should be free of most contaminants, and our 0 reading really does confirm that. Salt, sodium chloride, has a disproportionately large effect on the TDS meter because it is the salt of a strong base and a strong acid. That's sodium hydroxide and hydrochloric acid, which will dissociate nearly completely into sodium plus and Cl minus ions in aqueous solutions. Makes a lot of them available. Sugar and alcohol have minimal impact on the TDS meter because there is minimal ionization when they're in aqueous solution. They may be dissolved, but they don't ionize. Red dirt has a minimal impact because the inorganic mineral content, sand and other stuff, and organic material in the clay content don't dissolve or ionize easily in water. Our city supply tap water is relatively clean compared to most city water systems. But you can see the reverse osmosis system is effective at removing 90% of the ionizable contaminants. We went from 22 down to 2. It is reasonable to assume that if the reverse osmosis system is removing 90% of the ions, that it is also removing most of the non-ionizing contaminants. I hope you got some useful information out of this video. If you did, please like it, subscribe, and check out our other links. We'd really appreciate it. Thank you very much.